With genome sequencing technology becoming more widely available, researchers know ever more about variations and mutations in our DNA. Our body transcribes DNA code into proteins, including all mutations. The big question is, what is the impact of those mutations on proteins? We built the tool Aquaria as an accessible way for bench biologists to address this question. To understand how a protein functions, biologists need to be able to do two things. First, find and look at all related 3D structures, and second, map sequence-based features such as mutations onto these structures so they can see where the damage occurs. Aquaria is so easy to use that a researcher at one conference said, "Gee, this is like structural biology for monkeys." We designed Aquaria to be useful for all areas of biological research and education. Our audience includes researchers, educators, and students. The feedback we got so far indicates that Aquaria is filling a big gap in research tools. It empowers researchers to address questions that were too daunting before. We saw over 7,000 sessions within its first month of operation, and thousands of visitors each month since then. Our first design decision was to build a web-based tool. We wanted Aquaria to be accessible to everyone, instantly, no software to install. Then we had a requirements analysis. Which are the key questions biologists will need to address? We had detailed discussions with a range of scientists. They also showed us how difficult it was to use existing tools to address these questions. Then we had to come up with a scalable way to represent all the matching structures for a protein sequence, sometimes numbering in the thousands. Let's take a look.
To use Aquaria, we first specify a protein. In this case, let's choose P53, a protein implicated in many human cancers. After we specify a protein name and organism, Aquaria displays basic information about the protein, as well as a concise visual summary of all matching structures in the PDB with significant sequence similarity to the specified protein. For P53, we see that Aquaria finds 120 matching structures. From these, Aquaria automatically determines which structure has the largest number of identical residues when aligned onto the full-length protein sequence. This structure is then displayed at the top of the screen, and details about the structure are shown in the right-hand panel. The molecule is initially colored to indicate secondary structure elements, but this is augmented by dark coloring for residues in the structure that differ from the specified protein sequence. Clicking on one of these darkened residues lets us compare the amino acid occurring in the structure with that in the wild-type P53 sequence. We see that, in this structure, many residues differ from the wild-type P53 sequence that we initially specified. We may be more interested in other structures that have fewer changes. The matching structures section helps us here, since it ranks structures by sequence identity to P53. Let's look at this group of 87 structures. Clicking on the number opens a tree view where the structures are grouped by molecular configuration. We see here, for example, that 45 of these structures consist of a single molecule of P53 by itself, while other structures have P53 in complex with a range of different molecules. Let's choose a structure containing a tetramer of P53 bound to a dimer of DNA, which is believed to be one of the most important physiological states of P53. When we look at a complex structure such as this one, which contains many different molecules, Aquaria simplifies the view by automatically focusing on one molecule at a time. Clicking on the Features tab accesses a range of interpro and UniProt features, and clicking on a feature lane changes the molecular coloring, in this case highlighting the residues of P53 that are known to undergo a variety of specific post-translational modifications. Aquaria has been designed to make structured information easier to access and use, freeing researchers to focus on understanding and interpretation, and thus helping accelerate discovery in the life sciences.